All right, good morning, grade 9s. We're going to take a look at 6.4, which is all about triangles. Now, some of these things you might have seen before, and some of them might be brand new. But the one thing that we already talked about for triangles is about their interior angles, the angles on the inside of the triangle. Those inside angles will always add to 180 degrees. Now, that's true for any type of triangle. So whether it be a right triangle, isosceles, equilateral, scalene, etc., every single triangle will always have those three angles add together to equal 180 degrees. Now, we talked about naming angles before, which is kind of cool. Like, for example, this angle here, I could three-letter name it and call it angle CAB. But at the beginning of the unit, we talked about how when an angle is all alone, so there's no confusion of what that angle might be, there's not two or three angles with the same vertex, we could just call it by a single letter name. So this guy here is angle A, and this guy here is angle C, and this guy here is angle B. Remember, the capital letter alone refers to the point. So if we're talking about an angle, we need to make sure we have that angle symbol next to it. Now, what do you notice about the names of the side lengths? Maybe you notice that all of those letters are lowercase and not uppercase, not capital, which would be a great observation because capital letters are only there if they represent a point, and a side length isn't a point. It is the distance. It's the distance between 2 points. The other thing you might notice is that they're the same letters as our angles. Now, the last thing you might have noticed is that all of the lowercase letters are the sides that are across from the capital letter angle. So here I have big angle A, and little baby A is across from it. And here I have big angle C, and little baby C, that side length, is across from it. And here I have big angle B, and little baby B is the side length across from it. Now that's one way that we could name triangles. When we're talking about this type of naming, we would use this type of naming if there's no other shapes or angles or anything else to kind of make the diagram more complex involved. And you'll use this quite a bit in grade 10 as well. So let's just simply practice naming these three triangles. Can you pause the video and try and fill in the missing names of either the side lengths or the angles for these three triangles? Go. Okay, welcome back. I assume you paused the video. I assumed you did all the good things. So I have big angle A, and that will be across from side length little baby A. I have big angle R, and that'll be across from side length little baby R. And I have big angle T, and that'll be across side length little baby T. Okay, in the next triangle, we're given all side lengths. Remember, I can tell that they're side lengths because they're all lowercase letters. But again, the concept still applies. The lowercase f will be across from angle capital F. The side length E will be across from the angle capital E. And the side length little baby d will be across from the angle capital D. And the last but not least, we have a mix of angles and side lengths, provided we just have to fill out the rest. I'm going to start with the angles. I know this angle will be opposite side length little baby W. This angle V will be opposite side length little baby V. And this side length will be opposite angle capital U, just single U. Okay, So we're welcome to go ahead and name angles name angles in a triangle and side lengths in a triangle using this method. Okay, next, we've already kind of talked about this, so I just want to bring attention and remind you of it. But when we talk about congruent side lengths or congruent line segments, we use little matching tick marks to show that side lengths are congruent. So if I have the tick marks on these two sides, the same type of tick marks on both, I have matching ones, that implies that those two side lengths are congruent, or they're sides of equal length. Okay? When we talk about congruent angles, instead of tick marks, we use matching curved markings. And here we have matching curved markings. That implies that those two angles are of equal size. Those two angles would be congruent to each other. And we use that notation when we discuss different types of triangles, such as these ones. Now, you might have heard of these types of triangles before. If you have, great. If you haven't, that's okay. We're going to be talking about them now. But the first type that we're going to be talking about is called an equilateral triangle. Now, if we break down the word, we kind of have equa, as in like equal, and lateral. Now, maybe you've heard of the word lateral before. Maybe you haven't, but lateral is just like a normal English word. Lateral refers to the side. So down the road, when we talk about measurement, we'll talk about lateral area, and that will be like the area of the sides. But where you might have heard it before is maybe if you're ever in the gym or doing like exercises in a workout plan of some sort. Sometimes you'll have something like a lateral arm raise, where you're taking your arm and you're raising it to the side. Maybe you're doing a lateral jump, and that's where you're jumping to the side. So when we take a look at an equilateral triangle, we're talking about all of the sides, and as a result, all of the angles will be congruent or of equal length. Now I can see that in my diagram. I know that this is an equilateral triangle because all of the sides are congruent. They have those matching tick marks on them. And all of the angles are congruent because they have the matching curve markings on them. Now, it's cool that all of the angles will be the same in an equilateral triangle. But what's also cool is in an equilateral triangle, the angles will always measure exactly 60 degrees. Now, you don't have to write this down, but I'm going to talk a little bit about why that's true. Just on the side here. So I'm going to draw an equilateral triangle. So an equilateral triangle will have congruent sides and congruent angles. Now, I don't know the measure of this angle yet. I've told you it was 60, but let's pretend we have no clue what it is. And when we don't know when something is, we usually identify it with some unknown variable. So I'm going to use this little baby x to indicate the size of this unknown angle. Now, the thing I do know, is that all three angles are congruent. They're all going to be equal in size. So if I'm going to say this angle measures little x amount, then this angle will measure the same. And this angle will also measure the same. So I can use a little x to represent the unknown value of all three of the angles, since they're all the same anyways. Now, I also know that the angles in a triangle will always add to give me 180 degrees. So my first angle that measures x, plus my second angle that also measures x, plus my third angle that also measures x, will add to give me 180 degrees. Now, if I'm solving this, I know that my first step here is to simplify the left-hand side. So instead of x plus x plus x, I'm going to write 3x. And then I'm going to divide both sides by 3 to get x alone. And I end up with x is equal to 60 degrees. Now, if I ever wanted to show or prove or identify how I know that an equilateral triangle's angles will always equal to 60 degrees. This is how I can do it. But since I could do this for every single equilateral triangle, it is enough for you to just simply know that x, that angle value, that angle measurement, will always be 60 degrees. So if I give you a question about an equilateral triangle, I ask you to find the measure of an angle. You could show me this work, but you also could just know that every single equilateral triangle will have an angle measure of 60 degrees, so you could just jump straight to that answer. But this is why. I don't want you to just assume that I'm correct. I want you to know that it's right. So this is why equilateral triangle angles will always be or measure 60 degrees. Okay, the next type of triangle is an isosceles triangle. And again, if we're just looking at the diagram, I'm noticing I have two congruent sides because they have matching tick marks. And I have two congruent angles. Now, what I notice about the placement of those angles and the placement of the sides is, again, the whole opposite thing. So my congruent side will always be opposite my congruent angles. Because when we take a look at an angle, that's just how big two sides are when they open up from each other, right? So if you put your hands together to make it look like you're, I don't know, praying, I guess, and you open your fingertips to be wider from each other, kind of creating a V where the bottom of your palms of your hands are still touching, but your top fingers are spread apart. You could picture the V that you're making with your hands to be an angle. Now, open your hands to be about 90 degrees, okay? And when you do that, you'll notice that there's a certain distance between your two middle fingers from each other, right? Or your two fingertips from each other. Because the bigger you open the angle, the bigger that distance between your fingers is going to be. If you open your angle to be very, very small, the distance is going to be very small. If you open your angle to be very, very big, your distance between your fingers is going to be really big. Now, the reason why I'm talking about this is that imagine these are your hands right now. So hand 1 and hand 2, okay? If you open them up to a certain angle, and then you open them up to a certain angle that's the exact same size, your fingertips are going to be the same distance apart. Okay, so if you open up your hands to have the same angle or to create the same angle, the distance between your fingertips is going to be the same. So that's why when we take a look at an isosceles triangle, it's always the sides opposite that will be congruent from the congruent angles. And you'll notice that lone angle that's different will be opposite that lone side that's different as well. Okay. So it's going to say that two of the sides and the angles located across or opposite, whatever you prefer to write, from these sides are going to be congruent. Okay, next, we have a scalene triangle. Now I'm looking here at my diagram. I don't have any congruent side length markings, and I have no congruent angle markings either. So when I take a look at a scalene triangle, I will have no congruent sides, and I will have no congruent angles. And if I wanted to draw tick marks or curve markings in there, I could. I just need to make sure none of them match each other. So if I put a single tick mark on this side, maybe I'll go double on this side and triple on the other side, because all of those sides are different from each other. They are not the same length. And I could do the same thing with the angles. So this angle, I'll put a single curve marking on. This angle, I'll put a double curve marking on. And this one, I'll put a triple curve marking on, because I want to indicate that those three angles are also not congruent. It is not possible to have congruent angles in a triangle without having congruent sides, and vice versa. So if I have congruent sides, I definitely have congruent angles. If I have congruent angles, I definitely have congruent sides. But if I don't have congruent sides, I don't have congruent angles. Okay, last but not least, the right angle triangle. Now, a right angle triangle could be an isosceles triangle. It could, in theory, have two congruent sides and two congruent angles. So it's possible for these two sides to be congruent. And then as a result, the angles opposite them, so this guy would also be congruent. So it's possible to have a right angle triangle that is isosceles, but it's also possible to have a right angle triangle that is scalene, like the one in the image here. So when we talk about a right angle triangle, it could be a specific type of isosceles or a specific type of scalene triangle. Okay? Now, you would have seen right angle triangles a decent amount in grade 8 because you can do something cool with them. You can use the Pythagorean theorem, but this is only used to find the length of sides. And that's only when I have missing sides. Anytime we're talking about missing angles in a triangle, the only property we are using is that angles in a triangle will add to 180 degrees. We will never use Pythagoras to talk about angles. Pythagoras is only used to talk about side lengths. And it is also only used to talk about side lengths in a right angle triangle. So last year, you talked about Pythagoras. You talked about using that theorem, that a squared plus b squared is equal to c squared. But I'm willing to bet that every single triangle you saw was a right angle triangle. So you, in theory, used it for every triangle you saw. I cannot use it when I don't have a right angle in my triangle. It is exclusively only used when we talk about right angle triangles. Now, the other thing, when we talk about Pythagoras, this value of C and these values of A and B, they're just placeholders for numbers, right? I know that A, B, and C represent side lengths. First of all, they're lowercase. They are not capitalized. And I know that if I was talking about a vertex, I would have to use capital letters. So that's my first hint. But I know they're lowercase, which means I know their side lengths. And they're just placeholders for the numbers. So if I knew what the numbers were, I would substitute those in. Now, it really, really matters what C is. Now, C always is the hypotenuse. Oops, let's make that right here. The hypotenuse. Now, oftentimes, when you learn about the hypotenuse, you might have been told that it is the longest side in a right angle triangle. And that's true. Because if we think about it, the largest angle in a right angle triangle is the 90-degree angle. Because you can't have a bigger angle than 90s in that triangle. Because if you did, it would add up to more than 180, and that's not allowed. So the hypotenuse will always be the longest side, but sometimes it's hard to identify what that longest side is, because sometimes the hypotenuse and one of the side lengths look pretty similar, and if I don't have a number on both of them, it's hard for me to know for sure. So when we talk about the hypotenuse, I want to talk about how that hypotenuse will always be located across from that 90-degree angle. Which makes sense because the biggest side will be opposite the biggest angle. So it's located across from that right angle. So whatever that value is for C has to be the value of that hypotenuse. Now, I want to go and do one small little tangent here because I think it's important for us to talk about. Let's imagine if I had a right angle triangle. Here it is. And I have 3 vertexes, or vertices is the appropriate pronunciation. Okay? And I'm going to label them A, B, C. And I'm going to use my skills from naming triangle side lengths earlier and going ahead and naming those side lengths. So I know that capital A, angle A, will be across from side length little baby a. I know capital C, vertex C, will be across from side length little baby c. And I know capital B, vertex B, will be across side length little baby b. Now, this is probably one of the biggest things that I see grade 9s do incorrectly coming out of grade 8. Because we've learned that a squared plus b squared is equal to c squared. And since things are labeled as little baby a and little baby c and little baby b, we're like, oh, sweet, we'll just plug these in where they are. And that would actually be incorrect in this instance. And the reason being is that in our Pythagorean theorem, that c squared has to be the hypotenuse. And the hypotenuse of this triangle isn't labeled with a c. Doesn't mean it's labeled incorrectly. It is labeled correctly for what it is. But we do need to make sure that we are placing the right numbers in the right spots. So if I had some numbers, let's say this side length was 3 centimeters, this side length was 4 centimeters, and I don't know this side length, I would make sure to plug in the 3 and the 4 in the A and B spots. Even though this is labeled little baby c, it is not the hypotenuse, so it does not go in the C spot of my Pythagorean theorem. Okay? We're going to talk about doing examples with Pythagoras a little bit later, but I wanted to point that out, is that these are just placeholders for numbers. We could, in theory, use any letters in the whole entire world, but since we needed 3 of them, we're like, great, A, B, and C. It's not about the letters themselves. It's about the position of where those things get plugged in. Now, oftentimes when we're plugging things in, instead of plugging our unknown and leaving it as c squared, this hypotenuse is b. So I would actually typically plug in that unknown with the appropriate name. Okay, so I just wanted to point that out because we talked about labeling triangles with their angles and their side lengths. But that's a really common misconception, is that if it's labeled with a little c, it's got to be in the little c spot of the Pythagorean theorem, which is not necessarily true. Okay, what we're going to do is we are going to take some time and we are going to identify these triangles. Then we're going to solve for the missing angle measure, which is listed with a little baby x in there. I know that this is talking about an angle measurement, because it is literally tucked in and written inside the angle. And you might be like, Miss T, why didn't you, or how do I know that this little x doesn't represent a side length? A side length will typically be written in the middle of the side length, whatever it is, and with that lowercase letter, but it will typically be written on the outside. Whereas an angle, if I'm using a variable to represent an unknown inside my angle, I'll kind of tuck that on the inside of that angle crevice. Okay? Now, before we do these together, I want you to pause the video and I want you to try and identify the type of triangle in these 3 pictures. So is it equilateral? Is it isosceles? Is it scalene? Is it also a right triangle? That's what I'd like you to figure out. Okay? Go. And welcome back. Okay, so when we take a look at the first one here, I see this little small square in the corner, which is my big indicator that it would be a right angle triangle. Oops. It also has no congruent markings on the sides of any sort or on the angles of any sort. So this would also be a right angle triangle that is scalene. If I want to be specific, I could include both, but right angle is kind of good enough for now. If I'm taking a look at my next one, I'm noticing I have matching markings on 2 of the angles. Not 3, but 2. And when I have matching markings on 2 of the angles, that means I have an isosceles triangle. Now, something to kind of point out in my isosceles triangle is that if I have two congruent angles, I'll have two congruent sides. And those congruent sides will be opposite those congruent angles. So these two sides here would be congruent as well. It's not noted, but we can include that extra notation there to make it more clear to us. And then this last one here, again, I'm noticing little congruent markings on my triangle, which is awesome. There's two of them, which tells me that this one is also an isosceles triangle. It doesn't tell me about congruent angle markings, but that's okay. We can add those in because the congruent angles will be the ones that are opposite those congruent side lengths. Okay, now that I've labeled or identified each of the types of triangles, I'm now going to solve for the missing angle measurement, that little baby x value. Now, I know that that small square means it's a 90-degree angle in that corner there. So when I take a look at this, I have these three angles. I have my x, I have my 90 degrees, and I have my 53 degrees, and they add together to give me 180 degrees because the three angles in a triangle will always sum to 180. And so I'm simply going to add those together to get 180 degrees. And my job here is to go ahead and simplify. So I went ahead and combined 90 degrees and 53 degrees to get 143. I want to get x alone, so I'm going to subtract 143 degrees from both sides. And I end up with x is equal to 37 degrees. And I'm going to do the same process every single time I'm solving for an angle in a triangle. Is I'm going to take those three angles and I'm going to add them together to give me 180 degrees. Now you might think to yourself, hey, Miss T, I only know the value of kind of two of the angles here. I have x as one of the values and 46 degrees as the other. What about this guy? And that's where those markings come in, those congruent angle markings come in handy. Right? This angle is congruent to this angle. I could see that because the congruent angle markings are located there, which means that this angle must also measure 46 degrees. And if those two angles both measure 46 degrees, well then great. I will add both 46-degree angles together with my x to get a total of 180 degrees. And just like before, I'm going to simplify my left-hand side. So I'm going to add the 46 degrees and the 46 degrees, and I end up with, oops, not equals, plus 92 degrees. Right, so just that simplification step. And I want to get x alone, so I'm going to subtract 92 degrees from both sides. And when I do so, I get x is equal to 88 degrees. Okay, so when we take a look, first of all, we've done the work and things like that. But second of all, oftentimes when we take a look at our final answer, if a diagram is provided to us, our diagram will most often be not necessarily perfectly to scale, but like pretty close. And when I'm taking a look at this angle here, the one that I've just solved for, it looks pretty close to a 90-degree angle. It does look a little bit smaller if you're asking me, but it looks pretty close. And a 90-degree angle is 90 degrees, right? So 88 degrees seems like a really realistic answer, especially because that's so close to 90 and so close to what this value actually looks like. Okay. We have one more, and like, again, if we just want to predict in advance, this angle that I'm looking at is an acute angle, right? It is not 90 degrees. It is not more than 90 degrees. It's acute. It is less than 90 degrees. If I were to throw out a guess of how big that angle is, just by kind of in my head mentally understanding what the size of angles look like, if I'm thinking in my head that this is a 90-degree angle, okay, half of that is a 45-degree angle. I'm probably guessing that to be a little bit smaller than 45. Maybe it's in its low 40s. Maybe it's in its 30s. I don't have to guess accurately because I'm not a wizard. But if I have an idea of what my answer was going to look like or should look like, then I can, identify if I'm really off track, right? If I get an answer of 127 degrees and I'm like, buddy, it's acute, then I know that I made a mistake somewhere, okay? Anyways, let's do this last one. So this last one here, again, I'm only given two values of side lengths. I've given this x and this 115 degrees. But since I see the curve markings matching, I know that this other angle has to match. I don't know what that value was, but it's labeled as x, so this guy's also going to be labeled as x. So when I do my math, I get x plus 115 degrees, all adding together to give me 180 degrees. If I simplified my left-hand side, I get 2x plus 115 degrees is equal to 180 degrees. And I'm going to solve for x first by subtracting 115 degrees on both sides. You could use a calculator, but this could also be done using mental math. But when I subtract 115 degrees from 180 degrees, I get 65 degrees. And x isn't alone yet. I still have to divide both sides by 2. And when I do that, I get x is equal to 32.5 degrees. Now, when I look at my answer, that makes sense. It's an acute angle. And I said it was probably just less than half of a right angle. I guessed it was going to be less than 45. Now, did I know exactly how much less? No. But at least that number isn't ridiculous. I'm not being like, oh, this answer is 132 degrees, because that wouldn't make sense for an acute angle. Okay? So you can use your judgment to see if your answer is reasonable. Obviously, you can verify both sides, but it's hard to know if you're correct if you've made the equation and solved for it. Verifying just means you solved your equation correctly. It doesn't mean your original equation was correct itself. Okay, now, just like every other section in this note, in the notes, we've talked about that our final end game for this unit is to eventually have everything happen inside circles. So there are 4 more examples inside our circles that we are going to do the exact same thing for. We're going to identify them as equilateral, isosceles, scalene, right, etc. And we are going to solve for that little baby x, which is a little angle, because I could see that x is written in that small angle spot for each one. Now, before we get going with it, I just want to refresh our memories a little bit about circles. So here's a circle. We haven't talked a lot about circles yet, but let's imagine this green thing, this little dot, this point, is the center of a circle. There are likely 2 things of a circle you have identified before. The first being the distance from the center of the circle to the outside. And that can be anywhere of the circle from the center to the outside, anywhere of the circle from the center to the outside, anywhere of a circle from the center to the outside. Okay? And the second thing that perhaps you would have talked about before, again, if that little green point represents the center, is the distance across the circle hitting through that center point. And that could again be the distance across a circle at any point, as long as it goes through the center. Now, do you remember those words, those 2 words? There's one word to identify the pink lines that I've drawn in the first circle, and there's one word that we use to identify that white line, technically line segment, that I've drawn in that second circle. If so, think about those words in your head, but the pink line segments represent the radius. It's the distance from the center point of the circle to the outside. The white line segments I drew in the second circle, the distance across the circle going through the middle, is called the diameter. Now I want to focus on the radius right now. And the reason I want to focus on the radius is because the radius of a circle is the same distance no matter where I put it. Because that's actually how a circle is formed. I take a radius of whatever length I choose, I measure it out from the center point, and I get this. And I get these points all the way across the circle, around the circle, because I keep on drawing radii in all directions. And when I do that, I actually get all of the points that create a circle. But anyways, the point is that every single radius will be the same length or will be congruent to each other. Now, the reason I want to point that out is when we get into, for example, this question. This question has no congruent markings on my angles and has no congruent markings on my side lengths. But I can see that this side length here is a radius. It's the distance from the center of the circle to the outside. And this side length here is also the radius. It's the distance from the center of the circle to the outside. And as a result, since both of these represent radii, and the radius of a circle is the same everywhere, then we're going to have these two side lengths be congruent. And as a result, the angles opposite them will also be congruent. Okay. That's the only one I wanted to point out about. We don't really have any other radii that are two separate arms in the circle. Okay, we have a diameter here, which is made up of two radii, just in one straight line. But it's only one side of a triangle. It's not two separate sides, so we wouldn't mark them as congruent. But can you take a moment and label these four triangles as either isosceles, equilateral, right, or scalene? Pause the video and go. Okay, welcome back. So the first guy here, we have a right triangle. You could call it a right angle triangle. As long as you call it a right triangle, I'm happy, because I got that small square in the corner there. The second one, now that we've drawn in those congruent line segment signs, I can see that this is an isosceles triangle. Of the bottom two, there's no markings on any of the angles or sides here, but I can see the angles that I have are pretty drastically different, and there's no markings that I can either add or can see. So this one would just be scalene. And the last one, I see 3 congruent side length markings, so this would be equilateral. Now, just as before, we are going to find the measure of that missing side length, that little small x, or sorry, not the missing side length, the missing angle represented by that unknown value x. And we're going to do it in the exact same way. So we're going to add those 3 angles together to equal 180, and then we're going to solve for x. So again, can you please pause the video, try and do the math for all of these, and then unpause the video and watch as I kind of do it with you. And welcome back. Okay, so the first one, I'm going to go through as if you have already tried it on your own. So I know this one angle that's not labeled but has a small square is a 90-degree angle. And I'm going to add x, the 90-degree angle, and that 64-degree angle together to give me 184 degrees. When I simplify my left-hand side, I get 154 degrees when I combine those 2 angles. And I'm going to subtract 154 degrees from both sides. And when I do, I end up with x equaling to 26 degrees. Hope this wasn't too quick, as I assume that you have tried it on your own, but here we go. The next one. I'm labeled with this angle being X value and this being 111 degrees. But that last angle is not measured, but I know it's congruent to the other angle denoted with a small x. So I have x plus 111 degrees equaling to 180 degrees. I'm going to combine my left-hand side and I get 2x plus 111 degrees is equal to 180 degrees. And I'm subtracting 111 degrees from both sides. And when I do that, I get 2x is equal to, that's a great question. One of this, I get 59 degrees. And I'm gonna divide both sides by 2. So I get that final answer. When I get that final answer, doing some mental math here, half of 50 is 25, half of 9 is 4.5. So together, half of 59 is 29.5 degrees. Okay. Next, I've got my scalene triangle, and I'm simply adding those 3 angle measures together. I've got x, 57 degrees, and 39 degrees together. They add up to 180 degrees. I'm going to collect like terms on the left, and when I do that, I get, I get x plus 96 degrees is equal to 180 degrees. I'm subtracting 96 degrees from both sides to get x alone, and when I do so, I get x is equal to 84 degrees. Last but not least, I have an equilateral triangle. I could see that because I have all 3 congruent sides, which means all of my angles across from those congruent sides will be equal to each other. They'll be congruent. Now I can do the math and say x plus x plus x is equal to 180 degrees and solve for x. But if I identify it as equilateral triangle, I do not have to show my work to know that x is 60 degrees. Because as we spoke about at the very beginning, an equilateral triangle will always measure 60 degrees for each angle. Okay. Last but not least in this section is our Pythagorean theorem. Now, when we take a look at this, the main thing to identify here, or the main thing that we're going to be focusing here on, is going to be appropriately identifying your hypotenuse and appropriately naming the sides of our unknowns. So first of all, as a reminder, the hypotenuse is always going to be the side opposite the 90-degree angle. Can you take a moment and in these 3 triangles, can you highlight the hypotenuse, the side opposite the 90-degree angle? Go. Okay, hopefully you paused the video. Hopefully you did it. The side opposite the 90-degree angle is this guy. The side opposite the 90-degree angle is this guy. The side opposite the 90-degree angle is this guy. So, when we take a look at our hypotenuse, yes, it is the longest side, but it's hard to tell, especially in like the first and the last questions. Like, I don't have a number that goes here, so I can't just look at the numbers and pick the biggest one, because I don't have all 3 to be able to accurately compare. Okay. Now, in these 3 triangles, all of the vertices have been labeled with capital letters. Can you take a moment and label all of the sides using lowercase letters? Remembering that the side opposite an angle will be the same letter, just lowercase. Pause the video, try it out. And welcome back. Okay, so when I take a look at this, this side opposite angle E will be little e. The side opposite angle F will be little f. the side opposite angle D will be little d. Again, for the next triangle, the side opposite angle A will be little a. The side opposite angle B will be little b. The side opposite angle C will be little c. And last but not least, the side opposite angle G will be little g. The side opposite angle H will be little h. The side opposite angle I will be little I. Okay, now we are going to use the Pythagorean theorem. And when we do that, we know the Pythagorean theorem starts with a squared plus b squared plus c squared. A squared plus b squared is equal to c squared. And when we take a look at this, I know I'm using Pythagorean theorem because A, I have a right angle triangle for all three of these. There's not an isosceles or equilateral or scalene with no 90-degree in sight. To use Pythagoras, I need to have a right angle triangle, and I do for all three of these because I see that small square in each of those images. Now, I've identified the hypotenuse, and remember that the hypotenuse has to go in that C position. A and B doesn't matter because I'm just adding them. So whatever those values are, I can substitute in. So I'm going to put D and F in any order that I want, but I'm going to go 5 squared for A squared and 12 squared for B squared. And then I don't have a letter C as a side length in this question, but side length E is in that C position. So I'm going to replace C with that E value. The reason I'm replacing it is because the name is actually E. And I can't just change someone's name. Like if your name is Miss Thibodeau, you can't just come up and be like, you know what, you're Susan now. That's not how it works. If your name was little baby E, your name is little baby E. You can't just change it to Susan. You can't just change it to C. You have to keep it as is. Okay, and then I'm going to do the math. Questions like this one, you could do fully without a calculator. So if I gave you something like this on a CCA and there was no calculator, it would be totally cool. I'd give you nice numbers like these ones. You know 5 squared is 25. You know 12 squared is 144. And I could go ahead and simplify my left-hand side. When I add 25 and 144 together, I get 169. And luckily, 169 is a perfect square. And I'm going to square root both sides to get rid of the square on E. And when I square root both sides, I get 13 is equal to E. Now, we've learned from our solving equations unit that to have our final answer, we always want to have our variable listed first. So E is equal to 13. But the last thing we want to talk about is units, right? Our units for side lengths are measured in kilometers. So for our unit for our final answer of how long is side length little baby E, it's 13 kilometers. That's what km stands for. So just making sure, oops, that was not a highlighter. Just making sure that we have units on the end answer. Okay, we're going to do the same thing to the next question. So my Pythagoras is usually a squared plus b squared is equal to c squared. And just as we talked about at the beginning, these letters are just placeholders. I need to make sure that the hypotenuse goes in the C position. And if I'm looking at my question, my hypotenuse is actually little baby b in this particular question. And I have a number for it, which is great. It's 15 meters. But my other two sides are labeled A and C. They're going to go into these other two positions. The hypotenuse has to be where C is. You cannot change it, even if the triangle isn't labeled accordingly. So as we do this, I'm going to plug in a 9 for A. I don't know what the second side length is, so I'm going to replace it with its legit name, which is C. And then I'm going to replace C with 15. again, the hypotenuse has to go in the C position. Otherwise, the Pythagorean theorem does not work. You will not get the correct answer. Questions like this one, where the labeling is different than the actual original Pythagorean theorem, really screws with people. So I really want to make sure that you understand that what we've got has to go in specific spots, and we're not just filling in numbers or letters randomly. Okay, now I can do the math. 9 squared is 81. C squared is still C squared. 15 squared is 225. And I want to get C alone. When I do reverse BEDMAS, I have to get rid of addition first. So I'm going to subtract 81 from both sides. And I get C squared is equal to 144. And I'm like, C is being squared. To undo squared, I'm going to square root it. I'm going to do it to both sides. And I get C is equal to 12. And again, I'm looking for my units at the very end. 12 what? 12 meters. Because all of the other side lengths in this triangle are measured in meters. Okay. Again, this question I could give you without a use of a calculator. Obviously, for this whole unit, you can use a calculator, but be advised for like CCAs or things like that. This one would not require a calculator. This is all mental mathable. The last one, however, is not mental mathable. And you might think to yourself, whoa, we only have one side length. How am I supposed to solve for it? Like, am I solving for I? Am I solving for G? Je ne sais pas. But we're going to still try and figure this out together. I do notice there's some cool little tick marks here, which makes my life pretty happy, because that implies that whatever I is, G is the same thing. Little baby I and little baby G, they're the same because they are congruent to each other, so they'll have the same length. Or vice versa, little baby G will be the same as little baby I. Whatever they are, they're going to be identical. But again, let's just talk about what we know so far. So I know this is the Pythagorean theorem. Oops. A squared plus B squared is equal to C squared. I can use it because I have a right angle triangle and I'm finding a missing side length. Now the hypotenuse has to go into that C position, and I do have a number for that. So I know that 10 has to go where C is. And I and G would then go where A and B are. Now again, you might think to yourself, Miss T, how do I solve this? We've never solved an equation with two unknowns. And you would be correct. We have not solved an equation with two unknowns. But we can actually rewrite this to only have one unknown. And what I mean by that is, since little baby I and little baby G are congruent, I can replace little baby I with a G. Or I could replace a little baby G with a little baby I. Because the values of both of them are the same. They will be the same length. So what I'm going to do on this next line, instead of writing I squared plus G squared, I'm going to write G squared plus G squared. Because the number for I and the number for G would be identical. So I'm just going to represent them using an identical variable. So the same one. And I could only do this because those two side lengths are congruent, and I could tell using these matching tick marks. Now when I do that, it actually allows me to solve the rest of this. So just like if I had G plus G, I'd have 2G. If I have G squared plus G squared, I have 2G squared equal to 10 squared. And what's 10 squared? You all know. It's 100. Now, I want to get G alone. Right now, G is being times by 2, and it is being squared. Now, remember from last unit, we have to undo operations in reverse BEDMAS order. So I have to get rid of multiplication before I get rid of exponents. To get rid of multiplication, I use division. And I'm going to divide both sides by 2. And when I do that, I get g squared is equal to 50. The reason why we need to use a calculator in this question is because 50 is not a perfect square. So when I square root both sides to get g alone, I have to plug that into my calculator. When you plug it into your calculator, I'd like you all to plug it into your calculator. This question does say I want to round my answer to the nearest tenth, because if we remember from unit 1, the square root of any non-perfect square number will be irrational, which means its decimal will never end and it won't repeat. So my calculator will stop showing numbers after, let's say, 7 or 8 decimal places, but that's only because the calculator runs out of room. But the square root of 50, my answer will actually be irrational, but we're going to round it to the nearest tenth. When you round this to the nearest tenth, you should get 7.1. Again, I need to make sure I have units in my final answer. My side length before was measured in centimeters, so this is going to be measured in centimeters. And you might be thinking, but Miss T, we only solved for little baby g. What about little baby I? Remember, little baby g and little baby I were congruent. They would have the exact same length. So without doing any additional work, I also know that I would also measure 7.1 centimeters because they will have the exact same length because both side lengths are in fact congruent. Okay, and that's it for our 6.4 notes. I hope this all made sense, and I hope that you crushed the practice. Have a lovely day. Bye.